Uniform circular motion, UME physics past questions 1978 to 2003. So let's jump right in. We've got UME 1978 question number 11. The force required to make an object of mass m traveling with a velocity v turn in a circle of radius r is. Now we know that for circular motion, the force, the centripetal force F is equal to ma, where a is the centripetal acceleration, and centripetal acceleration is equal to v squared divided by r. So F is going to be equal to mv squared over r, and that should be option A, because we are told the force required to make an object of mass m traveling with velocity v turn in a circle of radius r. So the force that makes the object to turn in a circle, that force is known as the centripetal force, the center of seeking force. So the next question is UME 1982, question number 11. We are told the force responsible for holding the moon in its orbit around the Earth against the gravitational pull of the Earth is, of course, the force responsible for holding the moon in its orbit around the Earth is the centripetal force. The centripetal force is provided by the gravitational pull of the Earth, and that is option D. And it is not centrifugal. There's as a matter of fact, there's this misconception about centrifugal force that the force that there is a force acting opposite to this, which in the real sense doesn't really exist, but that is a story for another day. So we've got UME 1984, question number 26. A particle moves in a circular orbit of radius 0.02 meters. If the speed of the particle is 0.88 meters per second, calculate its frequency in circles per second. Now, if you think about it, the particle moves in a circle orbit of radius 0.02 meters. So the radius is 0.02 meters. If the speed of the particle is, so we've got the speed as 0.88 meters per second, and the radius is 0.02 meters. Calculate the frequency. So we are looking for the frequency. Now, how do we go about it? How we go about this is to look for the formula connecting V, R, and F. And I know from the pretty sure the first couple of formulas we come across in uniform circular motion. Now, the first couple of formulas you come across with in your uniform circular motion is V is equal to 2 pi FR. So we've got that. So because we know that V is equal to omega R, and omega is 2 pi F, or you can also write that as omega is equal to 2 pi over T, and T stands for period. So we've got V is equal to 2 pi F bracket 0.02. So, and all we got to do is make F the subject formula. So let me just write that over here. F is going to be equal to V, which is 0.88 divided by 2 pi times 0.02. F will be equal to 0.88 divided by 0.02. That is 44. So I've got 44 divided by 2 times pi is the approximate value is 22/7. So I've got 44 divided by 44/7, and I know you would know that 44, that would be 44 times the inverse of that, which is going to be 7 divided by 44, and 44 will cancel 44, that will be equal to 7. So I've got, we have 7 Earth's 7 cycles per second, which will be option B. Now to the next question, we've got UTME 1986, question number 16. A ball attached to one end of a string moves anti-clockwise around a circle whose center is O. If the string suddenly breaks when the ball is at point P, along which of the following paths will it move? And if you've studied circular motion very well, you know that the answer is going to be option B. And just so we know, the idea is that when normally, how do a body want to go? A body will always want to move in a straight line according to Newton's first law of motion. Remember from Newton's first law of motion, the only way a body, its states can be altered if it is acted upon by an unbalanced force. So normally this guy will want to go in a straight line, but if a force is acting on it in a perpendicular direction, let's just think of it that way for now, in a perpendicular direction, of course that's how it's going to be from circular geometry. Of course that's how it's going to be. So the force is gonna make this guy to turn. So you've got this body here. If this body is here, it's going to make it turn. So this force will be acting towards the center. That's why it's called centripetal force, that is center seeking. So so if this force is no longer there, what would you expect? You expect the force to obey Newton's first law of motion, which is going to act tangential to the direction of the circular path. So the option, or the correct answer, is option B. Not this guy, not this guy, not this guy. That is what's going to happen. So we have the next question, UTME 1994, question number 6. Which of the following is true of a particle moving in a horizontal circle with circular angular velocity? Now think about it. We've got a word here, constant angular velocity. Now I remember in secondary school when I was learning this topic, and yeah, it was okay, because I was like, I think the first time I learned this topic was through this through a textbook. Then I kind of get the idea at first, but it seems non-intuitive to me then. That was how it seemed to me then, because we all know that if a body is moving with a constant velocity, if a body is moving with a constant velocity or a constant speed, the acceleration will be equal to 0. That means the body is not accelerating. So, but this is the kind of motion that the body is moving with a constant velocity, a constant speed. Okay, let me just use the word constant speed now, and at the same time it's having acceleration. So, and the reason why that is because the body changes the direction. At this point, the direction which the velocity is in this direction, so the velocity is also in this direction. So because the velocity is changing, even though the magnitude of the velocity isn't changing, in other words, the speed is not changing, but because it's changing velocity, and acceleration depends on velocity, therefore the body is accelerating because there is a change in velocity, because we know that acceleration is change in velocity divided by time, or you can say change in time, however you want to think about it. But the idea is when this delta v is when the velocity is increasing. So for the body to be accelerating, that means the velocity is changing. So it's a kind of abnormalous motion, because it doesn't follow the normal regular way or intuitiveness of the regular motion. So even how good I was back then in secondary school with physics, I still had issues with this topic, and as I found out throughout my time of teaching through in different tutorial centers and stuff, I discovered that a lot of students have issues with this topic too. So what you've got to understand is that when we're talking about the constant angular velocity. We are not talking about the linear velocity. We are talking about the angular velocity, which will depend on the angular displacement now. So think about it. If this body is here, okay, let me start off from this place. Let me move in an anti-clockwise direction. If this body is here, now with reference, with using a polar position now, with reference to the center, this body is here, its displacement is 0. Now, if the body is here, it has been displaced through an angle of theta. Now, that is the angular displacement. We are not talking of linear displacement now, we are talking of angular displacement. So the first thing you've got to understand in your mind is that whenever we're dealing with stuff concerning angular stuff, circular motion, the first thing you've got to understand is the angular sticks with the angular. So the angular velocity or the angular speed, to be technical, we say, since we are using theta as angular displacement, the angular velocity is going to be angular displacement per unit time. So because velocity depends on displacement, so angular goes with angular, but linear goes with linear. Because if you watch my previous video on kinematics, linear motion, I talk about velocity being change in displacement per unit time, which also means displacement per unit time. So you either think of it as change in position per unit time or displacement per unit time. Now, I don't usually do much of explanation when it comes to solving questions on UTME, but I gotta go into this because it was until I understood this stuff that angular goes with angular while linear goes with linear, and the relationship between angular and linear is always v equal to omega r, whereby you also have linear displacement is equal to angular displacement r, and you've got linear acceleration equal to angular acceleration r. Until that concept was ingrained in my brain, that was when I was set free from this whole thing. So you've got to understand that angular goes with angular and linear goes with linear. So back to the matter is okay, we're told which of the following is true of a particle moving in a horizontal circle with constant angular velocity. So the energy is constant, but the linear momentum varies. Yes, this seems plausible. Let's check to the rest. The linear momentum is constant, but the energy varies. Nope, because think about it. Energy. Now, since the body is moving in a circular path, but the body is moving, that's the first thing we've got to know. Now, we know that kinetic energy is equal to 1/2 mv square. Now this v, in spite of the fact that we usually use the symbol v here, now this v actually denotes or connotes speed, not velocity. It is the speed. It depends on kinetic energy, depends on speed, not on velocity. So because kinetic energy is a scalar quantity, so it depends on the scalar quantity, which is speed, not velocity. So because the speed is always constant, the kinetic energy will be constant. But linear momentum, remember that linear momentum is mass times the velocity. Momentum is a vector quantity and it depends on a vector quantity, which is velocity. So if the velocity is changing, that implies that the momentum will be changing. So the momentum will vary. The momentum cannot remain constant. Recall, the body is moving with a constant velocity, therefore the kinetic energy is going to be constant. So the kinetic energy is going to be constant, but linear momentum will vary. So I believe we are good with option A. You can decide to go through the other ones with energy and linear and constant. Of course, you know this is one. Spin and linear velocity are both constant. No, the linear velocity changes while the speed is constant. So our answer for this question is option A. Now, UTME 2000 question number 7. We are okay for Romance figure 1. If velocity is constant, no, we know this is wrong. No work is done on the body. Yes, this is right. I'm still going to explain why this is correct. It has constant acceleration away from the center. Nope, the acceleration is not constant. To think about it mathematically, you may want to say, okay, the acceleration is constant. Yes, if you may want to think about it that way, that oh yeah, the acceleration is constant, but there's a word here that you've got to look for: away from the center. Nope, it is not away from the center. It is always towards the center. Now remember, I told you something about centrifugal, which most people think that that is the reaction force on the centripetal acceleration. No. You've got to understand that there is a difference between when you are dealing with second law of motion, Newton's second law of motion and Newton's third law of motion. There is quite a bit of difference there. But just like I told you, this guy does not really exist. Yes, it does in a sense because of the effect of inertia, because of the inertia that the body has got, but it is usually classified as a fictitious force because it doesn't really exist. So it is not always away from the center, it is always towards the center. So I'm pretty sure that is why this guy is wrong. Now, yeah, I'm back, and you guys must have noticed something, that the old stuff I've got written up here disappeared. They've all disappeared because when I was done recording this stuff, and I discovered that the microphone was already disconnected from me. So I was just talking. I didn't even know that the stuff has already been disconnected. So now I've got to do it again. So back to the matter. Enough of that. Now we've got 4. The centripetal force is directed towards the center. Yes, this is correct. So we've got this and this. The two are correct. So we've got the correct answer is option D. Now I think I said I was going to come back to why this is why there is no work done on the body. Now if you think about it, I've got this guy here, I've got the displacement here, displacement of the body in this direction, the force is acting towards the center, and from circuit geometry we know that this guy will be perpendicular to this guy. Whenever the force is perpendicular to the displacement, we know no work is going to be done, because we know that work done rather, just like I've done a couple of tutorials on it in my previous videos, that work done is equal to force times distance in the direction of force, or force times displacement, if you're still thinking about the same thing. So the force has to be in the direction of the force. In this case, since the force is not in the direction of force, no work is done. Especially, I've got to really put that right. If the force is perpendicular to the displacement, no work is done. The force might not be perpendicular to it, and of course work will be done. But whenever the force is perpendicular to it, no work is done. Because if you think about it, the component of the force in the direction of the distance is F cos 90 degree. And what is cos of 90 degree? Cosine of 90 degree is 0. So 0 times this, that is going to be 0. So no work is done for that. So that is why that is that. Now the next question is: a particle, UTME 2002, number 12, a particle in circular motion performs 30 oscillation in 6 seconds. Its angular velocity is, now we know that angular velocity is equal to 2 pi f. Now what is f? F is the oscillation in 1 second, but we've told that this guy makes 30 oscillation in 6 seconds. So for you to get the oscillation it makes in 1 second, of course that is going to be 30 divided by 6, which will be 5. So omega is going to be 2 pi times 5, which will be 10 pi radian per second, and that should be option that should be option C. But from what I can see here, there's no pi in there. I believe this must have been a typographical error. I'm not pretty sure about this, but if I were you and I'm in the exam hall, and I don't think there is negative marking, well, I'm not really close to any examiner for the Jamb board now, but if you do know about this, please let me know in the comment section. I don't think Jamb do negative marking, so if they don't, please just pick this is the closest to it. I'm pretty sure and I'm almost certain I made no mistake here, so I'm good to go. The correct answer is 10 pi radian per second. So but if I were you and I'm in the exam hall, I'm gonna check option C. So that is for that. So UTME 2003 question number 7. A piece of stone attached to one end of a string is well wound in a horizontal circle, and the string suddenly cut. The stone will fly off in a direction, of course, that is going to be tangential to the circular path, as I've as we've talked about this one in a previous question. And that is the end of this whole pack. This is as many questions as I could sort out with the past question materials I've got with me, how to arrange everything tight and do everything. So and I want you guys to like, share and subscribe, and I'll see you later. Take care.